So there was a question to show that in M2 of Z, by M2 of Z what we mean, the set of all 2 by 2 matrices, and of Z means we are allowed to use integer entries. All integers can be the entries inside. So what we showed over here, if I multiply 1, 2, 2, 4 by this particular matrix, I get the 0 matrix. Means what? This matrix being non-zero multiplied to a non-zero matrix, we are getting a 0 matrix. Means this is a 0 divisor. This matrix is called as 0 divisor. Followed it? I suppose you got it. Yesterday I told you to find out the answer, and here itself I have given the answer. Is it okay? All right. Now the one more question was asked yesterday. In Z6, you were asked to solve the equation x square plus 2x plus 2 equal to 0. So you can see I tried with variety of, all the elements of Z6, and we found this is not a 0 anywhere. X square plus 2x plus 2 for none of the elements happens to be 0. So this equation has no solution in Z6. I suppose you followed it. Is this okay? So what you observe? This equation has no solution in Z6. Same way we tried for this equation, x square plus 2x plus 4 equal to 0. And I found that x equal to 2 gives me answer equal to 0. Rest all are non-zeros. So x equal to 2 is the solution. So you will work out on your own and check whether I am correct or not. So with this, I would like to move next. Hope all of you are ready for the next thing. Yes. And now I would like to go back. And I will share my screen now. Yes, now we will start with the field of quotients in an integral domain. Field of quotients in an integral domain. So let us directly start with. So this is the preliminary thing. See, if I have cross product of two sets, we get the ordered pairs as you are noting over here. So in this case, what we are doing is we are taking ordered pairs. Set S contains ordered pairs AB, where A and B are members of an integral domain. D stands for integral domain. And what condition we are putting on it? B must be non-zero. This is the condition. Set S is taken. I would like to highlight the statement. Set S is taken this way. S is nothing but D cross D. And only what we are avoiding, the second place we are avoiding to be 0. Means complete D cross D is not taken. It is the subset of D cross D. The second place 0 is avoided over here. Okay. Now we want to check when to say two elements are equivalent. Ordered pair AB and ordered pair CD, when they will be equivalent. We can't say equal, but we will say equivalent. So when they are equivalent, so if first coordinate of the first element multiplied to last coordinate of the second element equals the second coordinate of first multiplied to the first coordinate of the second. So AD is equal to BC. If you get A times D, I would like to draw it for you. I multiply A to D and B to C. And if this product happens to be same, then we say that the ordered pairs are equivalent ordered pairs. Now, we want to show that this relation tilde, this relation, is an equivalence relation. How would you check that the relation is an equivalence relation? So you have to go for reflexivity, symmetry, and transitivity. If you talk about AB, then very directly you can check A multiplied to B and B multiplied to A, you get the same answer. AB is equal to BA. So multiplication is commutative in an integral domain. And that is why AB is equal to BA. We got reflexivity. Talking of symmetry, if suppose AB is congruent to CD, I mean equivalent to CD, then what will happen? This means AD is nothing but BC. Now what I want to interchange their places. So instead of reading this way, let me read as BC is equal to AD. BC is equal to AD. So what will happen? How I'll write those pairs? So C I'll bring in first place. D let me have in the last place. And we mean to say equivalent. Now you decide these places. C multiplied to the last. What is it? B. So B must be here. I hope you are following me. C multiplied to B must be equal to D multiplied to A. So did we get the places interchanged? AB equivalent to CD. It has given us CD equivalent to AB. So it is a kind of symmetric relation. The relation is reflexive as well as symmetric as you are watching. Now what is there? We want transitivity. If suppose AB equivalent to CD and CD is equivalent to RS, we mean to say that AB is equivalent to RS. So let us go. I erase this. Okay, I would like to now go with the next. All right. So first we are saying AB equivalent to CD. What it means? AD is equal to BC. What else is given to you? And you are saying CD is equivalent to RS. So CS will be equal to DR. This is what you are getting. CS is equal to DR. Okay. Now what you want to show? You want to show that AS is equal to BR. AS is equal to BR. So how would you reach to that? So what we'll do is we'll have some common ground over there. So in this two, what common ground you'll find? So there is a CS over here, and here you are having BC. Or AD is there, DR is here. So accordingly, let us multiply AD, this equation, by S. So let us multiply it by, let us change the color. So let us multiply here A S D. What you will get on the right hand side? It will be B S C. The equation we multiplied throughout by S. Now what we will do is to CS, let us multiply by B. So that you will get BSC. So here let me multiply by B. And here again I multiplied by B. So what happens? This part BCS and BSC, they are same. So what we'll do is we'll equate the corresponding sides. If I equate the corresponding sides, what do I get? Left side here I found was ASD and the right hand side there was BDR, and you can check D is common and you are dealing with an integral domain. Okay, in case of integral domain, you can cancel because integral domain is without zero divisors. And if there are no zero divisors, then cancellation law holds. And because cancellation law holds, I can cancel this D. D is cancelled. Actually, it is commutative. So D is cancelled over here. And what you got is AS is equal to BR. Because of commutativity, I can do so. And I can write here AB congruent to, equivalent to RS. As you know, the multiple of A will be in the last place and the multiple of B will be in the middle place. And that is why AB equivalent to RS you have shown. And thus you have shown that it is transitive also. We began with AB equivalent to CD and CD equivalent to RS, and we are reaching to the fact that the first is equivalent to the last. So we have shown that it is transitive, and that's why we could show that all the three are there, and so it is an equivalence relation. So tilde defined this way is an equivalence relation. Okay, so if it is an equivalence relation, I can define an equivalence class on S. What is set S with S? Let us recall. Set S is nothing but the set of all ordered pairs AB such that A and B are members of the integral domain, belong to D, and only B cannot take the value 0. That is the only condition that we put. Second place is not a 0. So this is nothing but our set S. Now can we define equivalence class? What is an equivalence class? So if I select any pair AB from this particular set, then the equivalence class is either denoted by box or is denoted by bar. So you may have bar overhead, ordered pair AB and bar overhead. So this is an equivalence class of AB, or you prefer box. So in this particular textbook, they prefer box. What is this box? It tells you that this contains all ordered pairs XY from S belonging to S. How are they? Such that AB tilde XY. So those pairs which are equivalent to AB form the equivalence class. So this is what you have. I feel you are getting. So we are now interested in the set of all equivalence classes, and we are going to show that the set of all equivalence classes is nothing but the field. So we are going this way. All right. Now let us deal with the lemma. Let us deal with the lemma. For equivalence classes AB and CD in F, these equations, equivalence class of AB plus equivalence class of CD is nothing but equivalence class of AD plus BC comma BD. So how addition is defined? You take AD plus BC in the first place and product of the second entries are in the second place. As if I would like to remind you, you were having A by B plus C by D. How do you perform this operation? How do you perform? You take product of the denominators. So this is BD here. In the numerator, you write AD plus BC. I hope all of you agree. So the first place is AD plus BC and the second place is nothing but the denominator. So here all the ordered pairs that we are dealing are in this fashion. The first entry is the numerator and the second entry is the denominator likewise. And how they are defining multiplication and on these equivalence classes. So multiplication of the equivalence classes, numerator multiplied to numerator and denominator multiplied to denominator. So A by B multiplied to C by D. What will produce? This will produce AC in the numerator and BD in the denominator. So I suppose you followed me. Have you followed these definitions? So followed the definition. Okay. See here what they are trying to do. Actually, it is described in this particular description. The integers are contained in the field Q. I would like to go with highlighter. Let me go back. The integers are contained in the field Q whose elements can all be expressed as quotients of integers. So same thing we are following over here. If you read this, concentrate to this statement, you'll come to know what is going. So S is the set containing ordered pairs AB. A and B are members of the integral domain. Only exception is B is not a zero. Non-zero entries in the second place. Why? Because they are as good as our denominators. Okay. And we just tried how to add two equivalence classes. So what we do is we follow this technique and have to multiply two equivalence classes. So we are following this one. Fine. Hope you are following me. Can I go ahead? Okay, only one response. Okay. All right. I continue. So see, this lemma tells you that if I define this kind of operations, then these operations are well defined. What do you mean by well defined operations? What is a well defined operation? So if I add this way, then the result is actually back in my set and there is, so let us one by one, let us see this. Observe first that if equivalence class of ordered pair AB and equivalence class of ordered pair CD are in F, then ordered pair AB and ordered pair CD are in S. So B is not 0 and D is not 0. Because D is an integral domain, product BD is also not 0. Because you know what is an integral domain? Integral domain contains no zero divisors. So product of two non-zero numbers will not be non-zero. I repeat my statement, there was a bit mistake. Product of two non-zero integers will always be a non-zero number. Product of two non-zero elements will be a non-zero element. If product happens to be zero, we call them as zero divisors, and we don't have any zero divisors over here. So I think I'm proper over here, and I think you got it. So what will happen? This BD will never be zero. In this case also, so both elements belong back to your S. And this shows that the right hand sides of the definition give elements back in F. Now it remains to show that these operations of addition and multiplication are well defined. That is, they were defined by means of representatives in S of elements of F. So we must show that if different representatives in S are chosen, the same element of F will result. So what we have done, we have taken ordered pair A1 B1 from the equivalence class of AB, and C1 D1 is chosen from the equivalence class of CD. So what happens if I add like this? This element is back in this set, A1 D1 plus B1 C1. So it is of the same pattern that we discussed here, of the same pattern. And of course, it will be in this equivalence class. Again, A1 C1 comma B1 D1, it is again of this pattern, and that is why we are giving by suffixes so that easily we can understand. We had AD plus BC, so in its place we are having A1 D1 plus B1 C1, and here we had BD, so it is B1 D1, so we are on the same lines, and that is why it is well defined. So same kind of thing you can see. All right. So we have tried to show that this is back in the equivalence class. Now it is our duty to show that all the field actions hold with these definitions, and that is why we are going ahead. We started with the definition of addition and multiplication is well defined, and now we want to show that addition is commutative, because what we need for a ring, basically the sage along with addition is an abelian group. For that, we started with, first of all, well-definedness of the operations and binariness. Now we are talking about commutativity. You add two equivalence classes, then it is of this pattern. So reverse way, even if you go, you get the same kind of thing, and that is why this operation is commutative operation. I feel you know this very well. AD plus BC is the same as CB plus DA, and BD is equal to DB. Why for? Because as far as D is concerned, D is an integral domain. So what is an integral domain? A ring, commutative ring with unity without zero divisors. I repeat, commutative ring with unity without zero divisors. So here you got commutativity. AD you can have DA, BC you can write as CB, and you got the same result as the earlier one. Followed me? Now, addition is associative, that is by default, so no question of this. What is the identity element? By what number if I multiply? I mean identity for addition. Ordered per AB plus what? Will give back AB to me. I want this to
Zero,
be
zero.
no. So we have to go with this. How do we actually multiply? So first place into the last place, isn't it? And the middle places are multiplied together. So I would like to change the ink. You can see A multiplied to 1 will produce A, and plus B into 0. I suppose it is so. What I mean to say is A into 1 plus B into 0. This result will produce A. Is it back A? I feel you followed. First place into last place and the product of the middle places and then the addition. So we got it. And what about the second place? How do we define second place? Second place is simply the multiplication of the second places. B into 1 is B. Got back AB? Followed the operation?
Yes, madam.
Okay. I would like to revise it because very less response I got. Okay. See, Equivalence class of AB plus equivalence class of CD. How do we define? It is the equivalence class of this kind of element. First place multiplied to the last and the middle are multiplied together and added. So to get back AB, what I have to do? A multiplied to the last place. I want my A to return. So here I need 1. And plus nothing I want. So I take here a 0. So A into 1 plus B into 0 gives back A to me. And how to define the second place? Second place is just the product of the second places. So B into 1 will be B. So I got back my AB. Followed now? Okay, still one more response I got, but okay, okay. Now, I would like to ask you, 2, 5 and plus I want to add, suppose 3, 2. So what this product will be? I'm sorry, what will be this addition? I said product. It is addition. So it will be 2 2s are 4 plus 5 3s are 15. So first place will be here 4 plus 15. Hope all of you agree. And the second place will be 5 2s are 10. So what is the answer? This is 19, 10. Followed me? Answer is 19, 10. Or in other words, I would like to go this way, which is quite familiar to us. How do we add here? What it should be? 2 2s are 4 plus 5 3s are 15. I got 19 in the first place. And this is 5 2s are. Followed me? 2 2s are 4 plus 3 5s are 15. This is 19. And 5 2s are 10. This is what you are getting. As usual, you just add two fractions. Same kind of thing we are dealing here. Okay. So this way you are adding. I think you followed me. And that is why. What should I add to 2 by 5 so as to get back 2 by 5? What should I add to 2 by 5 so as to get back 2 by 5? Yes, anybody? It's but natural that denominator cannot be 0. I want back answer as 2 by 5. So I need 5 into 1 as 5. Followed me? Why denominator is 1? Is it fine? Denominator should be 1. 5 ones are 5. Now what you will do? 1 2s are 2. Plus 5 words are will give me 2. So here I need a 0. What happens? 1 2s are 2. Plus 5 zeros are 0. 2 plus 0 is 2. Got it? So additive identity is nothing but a 0. I can read my 0 as a 0 upon 1. This is what we are saying. This is additive identity. Is it okay? So this kind of addition is nothing but the addition that we always follow in case of fractions. In case of fractions, we add like this. What we do? The product of the denominators is over here. The denominator of one number multiplies to the numerator of the other and vice versa. And then we add them. Do you know this very well? So same technique we are following here. So 0 upon 1 If added to any number, the number will remain the same. And that is why it is called as an identity element. Now, what will be the additive inverse? What will be the additive inverse? Very directly, what will be the additive inverse? If I have A upon B, I will add something to this so that the answer will be 0 by 1. So what should I add to this? I said A by B plus something should produce 0 by 1. So when is it possible? So denominator is same and numerator is negated. What it produces? Denominator square by our definition. And this B multiplies to A produces AB here. Plus this is minus AB, meaning AB minus AB. And you can read this out as 0. And 0 upon B square is equivalent to 0 upon 1. 0 upon B square is equivalent to 0 upon 1. Do you agree? When do you say two elements are equivalent? I got answer at 0 comma B square. I want to check whether it is equivalent to 0 comma 1 or not. How do I do so? The same technique, I multiply the first entry to the last entry. 0 into 1. This was B square. And the middle entries I multiply. So B square into 0. What is the answer on both the sides? 0 into 1 is 0 and B square into 0 is also 0. So did you find the equivalence of these two numbers? Okay, so I think you might have got that the inverse of A by B is minus A by B. And that is why we are writing this way. Equivalence class of ordered pair minus AB is the additive inverse of equivalence class of ordered pair AB. Now multiplication is associative, so we know better multiplication is associative. Multiplication in F is commutative. Distributive laws hold because nothing different thing we are doing over here. And what will be the multiplicative identity? If I multiply A by B, I should get back A by B. How do we multiply? Numerators are multiplied together, denominators are multiplied together. So A into 1 produces A, B into 1 produces B. So 1, 1 is the multiplicative identity. And the last thing that we require, the equivalence class of AB, if it belongs to F, is not additive identity element, then A will be non-zero in D, and equivalence class of BA is the multiplicative inverse for AB. Yes. So multiplicative inverse must exist. What is the multiplicative inverse of AB? It is nothing but B by A. But when I say AB belongs to the set, I have assured that B is non-zero. So here you have to mention that A is also non-zero. So if A is non-zero, then and then only it will have inverse. And the answer is 1 by 1, which is our multiplicative identity. So multiplicative inverse of AB is nothing but BA provided A is non-zero. This is the very important condition. If A is non-zero, then only we will think of its multiplicative inverse. Followed me? So in a field, every non-zero element has multiplicative inverse, then only we call it as a field. So it is an integral domain, and moreover, every element is having inverse. Every non-zero element is having inverse, then we call it as a field. So this way we have shown that all the field actions hold, and that is why it becomes a field. I suppose you followed it. Once again, you'll go through the video and check what we have up till now discussed. I think that is sufficient for today.